In the stillness of deep space, beyond the glare of city lights and the shimmer of our atmosphere, a machine floats in silence, collecting photons that have traveled for billions of years. If you have the time, maximize your screen. Let the scale of this story settle in. And if this kind of exploration speaks to you, subscribe so we can continue building these journeys together. What follows is an investigation into a claim so extraordinary that it challenges the very grammar of cause and effect. The James Webb Space Telescope, we are told, has captured matter moving backwards in time. Not merely observed something ancient, not simply peered into the distant past as all telescopes do, but witnessed material itself reversing its temporal trajectory, defying the arrow that points from yesterday toward tomorrow. To understand what such a claim could mean, and whether it could possibly be true, we must begin not with spectacle, but with precision, not with wonder, but with the painstaking work of defining terms, understanding instruments, and separating observation from interpretation. A telescope does not see in the way a human eye sees. It does not comprehend or interpret in real time. What a telescope does at its most fundamental level is collect electromagnetic radiation, photons, and focus them onto a detector that records their arrival. The James Webb Space Telescope, positioned at the second Lagrange point approximately 1.5 million kilometers from Earth, is an infrared observatory. Its primary mirror, a hexagonal assembly of gold-coated beryllium segments spanning 6.5 meters, gathers infrared light ranging from wavelengths of about 0.6 microns in the orange-red part of the visible spectrum to 28.5 microns deep in the mid-infrared. This light, once collected, is directed into 4 science instruments: the near-infrared camera, known as NIR-CAM, the near-infrared spectrograph, or NIR-SPEC, the mid-infrared instrument called MIRI, and the fine guidance sensor / near-infrared imager and slitless spectrograph, abbreviated as FGS / NIRISS. Each of these instruments is a marvel of engineering, but none of them can see time directly. They can only detect photons, count them, measure their wavelengths, and record when those photons struck a pixel. Time enters the picture only as metadata: the timestamp of the observation, the duration of the exposure, the sequence of frames if the target is monitored repeatedly. When we speak of capturing something, we mean recording an electromagnetic signal. When we speak of matter, we mean particles with mass, or the energy fields that manifest as matter, distributed across space and evolving across time. When we speak of motion, we mean change of position with respect to time. And when we speak of backwards in time, we enter territory that requires extraordinary care. In everyday language, backwards in time evokes images from science fiction: a film reel spinning in reverse, a dropped glass leaping back to the countertop hole, a living organism growing younger. In physics, however, the phrase must be operationalized. Does it mean a violation of causality, where an effect precedes its cause? Does it mean a trajectory in space-time that loops back on itself, a closed, time-like curve? Does it mean matter with negative energy density that would be required by certain exotic solutions to Einstein's field equations? Or does it mean something more mundane, an observational illusion, a projection effect, a misalignment between coordinate systems, a data processing error, or a misunderstanding of what was actually observed? To approach this question responsibly, we must first establish what observations are possible and what they imply. The James Webb Space Telescope is designed to observe the universe primarily in the infrared portion of the spectrum, because infrared light can penetrate dust clouds that obscure visible light, and because the expansion of the universe stretches the light from distant galaxies into the infrared through cosmological redshift. When Webb observes a galaxy 13 billion light years away, the photons arriving at its detectors today left that galaxy 13 billion years ago. In this sense, all telescopes are time machines that show us the past. The more distant the object, the further back in time we see it. This is look-back time, a straightforward consequence of the finite speed of light. Light travels at approximately 299,792 kilometers per second in a vacuum. And because the universe is vast, the light from distant objects takes billions of years to reach us. When Webb captures an image of a primordial galaxy, it is not observing that galaxy as it is now, whatever now means across such cosmic distances, but as it was when the universe was young. Look-back time, however, is not time reversal. Observing the past is not the same as witnessing the past unfold in reverse. When we watch a recording of an event, the recording plays forward even if the event happened long ago. The photons from that distant galaxy have traveled forward in time from their emission to their detection. The processes within that galaxy, star formation, supernova explosions, gas flows, also proceeded forward in time according to the arrow of increasing entropy. So if the claim is merely that Webb has observed something very old, that is not extraordinary. Every deep field image Webb produces is a portrait of ancient light. But the claim is not about age. The claim is about motion backwards in time. This implies that somewhere in the data, there is evidence of a process or trajectory that reverses the usual temporal sequence. To evaluate this, we need to understand what kinds of motion Webb can detect and how motion is inferred from astronomical data. Astronomical objects are almost always too distant for their motion across the sky, their proper motion, to be detected in a single image or even over the span of weeks or months. The exception is within our own solar system, where planets, asteroids, and comets move noticeably against the background stars. For stars within our galaxy, proper motion can be measured over years or decades, appearing as a slow drift across the celestial sphere. For galaxies and quasars, proper motion is generally negligible. They are so far away that even high velocities translate to imperceptibly small angular changes over human timescales. Instead, motion in distant objects is inferred in two primary ways: through Doppler shifts and through time-resolved changes in brightness or structure. The Doppler shift is a change in the observed wavelength of light due to relative motion between the source and the observer. If an object is moving toward us, its light is blue shifted to shorter wavelengths. If moving away, red shifted to longer wavelengths. Webb's spectrographs can measure these shifts with high precision by comparing the observed wavelengths of spectral lines, characteristic fingerprints of elements and molecules, to their laboratory rest wavelengths. From the magnitude of the shift, the radial velocity, the component of motion along the line of sight, can be calculated. A positive redshift indicates recession. A negative blue shift indicates approach. This is motion in the conventional sense, an object changing its distance from us as time progresses forward. There is nothing inherently time-reversed about it. Even if an object is approaching us, it is still moving forward in time. Its distance from us is decreasing as time increases. Time-resolved observations add another dimension. If Webb observes the same object multiple times over hours, days, or months, it can detect changes in brightness, color, or spatial structure. Variability in brightness can indicate intrinsic changes in the object, such as a star pulsating, a supernova brightening and dimming, or a black hole's accretion disk flickering as material spirals inward. Structural changes might reveal a jet of plasma extending from a galaxy's core, a cloud of gas expanding from an explosion, or the proper motion of nearby stars. By comparing images taken at different times, astronomers can construct a time sequence: frame 1, frame 2, frame 3. The natural assumption is that these frames are ordered by increasing time. Frame 3 shows the state of the object at a later time than frame 1. But what if the observed sequence seems to contradict the expected temporal order? What if the changes between frames suggest that the object's state at a later time is inconsistent with causality flowing forward? Imagine, for instance, observing an exploding star. In the normal course of events, we expect to see the explosion begin, brightness increase as the shock wave propagates outward and energy is released, and then a gradual dimming as the ejecta expand and cool. If instead the observations showed the star brightening over time in a manner inconsistent with any known physical process that runs forward, perhaps brightening in a way that would require energy to flow from a later state to an earlier one, that might superficially appear as time running backwards. But this is where caution is essential. An unexpected brightness curve does not automatically imply time reversal. It might indicate an unknown astrophysical mechanism, an intervening process such as light echoes, where light from the explosion reflects off surrounding dust clouds and arrives at different times, or a gravitational lensing effect where light from different moments in the explosion's history is bent around a massive object and arrives at our telescope out of sequence. Gravitational lensing, predicted by Einstein's general theory of relativity and confirmed by observations, occurs when a massive object such as a galaxy or cluster of galaxies bends the path of light from a more distant source. The light follows curved geodesics in the warped spacetime around the lens. In many cases, multiple images of the background source are produced, each corresponding to a different light path with a different travel time. This leads to a time delay. Light traveling along the longer path takes more time to reach the observer than light traveling the shorter path. If the background source is variable, such as a quasar that flickers, the different images will flicker at different times, each showing the intrinsic variability offset by the differential light travel time. To an observer watching the different lensed images, one image might brighten, and then, days or weeks later, another image of the same object brightens in the same way. This is not the object moving backwards in time. It is the same event being viewed via two routes, with one route taking longer. Yet, if the time delays were misunderstood, or if the lensed images were not recognized as such, an observer might mistakenly interpret the later brightening as an earlier state of the object appearing after a later state, creating the illusion of reversed temporal sequence. Webb is particularly well suited to observing gravitationally lensed systems because its infrared sensitivity and angular resolution can resolve fine details in lensed arcs and multiple images. Several of Webb's early science targets included galaxy clusters that act as gravitational telescopes, magnifying and distorting background galaxies. In these systems, The time delay between images can range from days to years depending on the geometry and mass distribution of the lens. Careful modeling of the lens can predict these time delays, and by monitoring the brightness of the multiple images, astronomers can test those models and measure the properties of the lens, including its mass distribution and, in some cases, cosmological parameters such as the Hubble constant. But suppose the modeling were incorrect. Suppose the light curves were analyzed without recognizing the lensing. The observed sequence of brightness changes might then seem causally inverted. A flare in one image followed by a flare in another image that, if misidentified as the same location at a later time, would suggest the object returned to an earlier state. This would be an interpretive error, not a physical phenomenon. The light itself still traveled forward in time along each path. The photons were emitted, propagated, and detected in the usual forward sequence. The reversal would be in the narrative constructed from the data, not in the data itself. To claim that matter is moving backwards in time, one would need evidence that goes beyond an unusual light curve or a confusing image sequence. One would need to demonstrate that the physical processes governing the matter violate the second law of thermodynamics, which states that the entropy of a closed system tends to increase over time, or that causality itself is violated. The second law is not a fundamental law in the same sense as conservation of energy or momentum. It is a statistical law arising from the overwhelming probability that systems evolve from ordered states to disordered ones. A broken glass does not spontaneously reassemble because the number of microstates corresponding to a broken glass vastly outnumbers those corresponding to an intact glass. Time's arrow, the asymmetry that distinguishes past from future in our everyday experience, is deeply connected to this entropic increase. If matter were truly moving backwards in time, we would expect to see entropy decreasing locally, order emerging spontaneously from disorder, and effects preceding their causes in a manner that could not be explained by hidden variables or advanced boundary conditions. In the context of Webb observations, what would such evidence look like? Suppose Webb were observing a cloud of gas around a star, perhaps the remnants of a previous outburst. In the forward direction of time, we would expect the gas to expand, cool, and gradually mix with the surrounding medium, increasing in entropy. If time were running backwards for that gas, we would see it contracting, heating, and separating into distinct, more ordered structures, with the light emitted in a sequence that reverses the usual thermodynamic progression. But even this is not sufficient to prove time reversal because many astrophysical processes involve contraction and heating. A collapsing protostellar core, for instance, contracts and heats as gravitational potential energy is converted to thermal energy. This is entirely consistent with forward time and increasing entropy when the larger system, including the radiated energy, is considered. The entropy of the infalling gas decreases locally, but the total entropy of the gas plus the radiated photons plus the surrounding environment increases. True time reversal would require the global entropy to decrease, or a violation of causality that could not be accounted for by considering a larger system. Causality, in the framework of relativity, is protected by the structure of spacetime. Events are related by causal relationships if they can be connected by a signal traveling at or below the speed of light. The future light cone of an event contains all events that can be causally influenced by it. The past light cone contains all events that could have influenced it. For time travel or backward causality to occur, there must be a closed time-like curve, a path through space-time that loops back on itself, so that an observer traveling along this path would return to an earlier time. Such curves are mathematically possible in certain solutions to Einstein's equations, such as the Gödel universe, the interior of a rotating black hole described by the Kerr metric under certain conditions, or the space-time around a traversable wormhole with exotic matter. However, these solutions involve extreme conditions and often require matter with negative energy density, which violates the weak energy condition and has never been observed. Furthermore, the existence of a mathematical solution does not guarantee its physical realizability. Many physicists suspect that quantum effects or unknown principles of quantum gravity would prevent closed time-like curves from forming, preserving causality even in the most exotic environments. If Webb were to observe matter moving backwards in time in a fundamental sense, it would need to detect signatures of such exotic space-time structure. This might involve observing light that appears to arrive before it was emitted by clocks that should agree on time ordering, or detecting particles whose trajectories loop back in time when reconstructed in a consistent coordinate system. The difficulty is that Webb does not measure space-time curvature directly. It measures photon arrivals and wavelengths. Inferring the geometry of spacetime and the causal structure of events requires a model, assumptions about coordinates, and careful cross-checks. Any claim of observed time reversal would need to rule out all conventional explanations, optical illusions, lensing, instrumental artifacts, coordinate confusion, and misidentification, before invoking a breakdown of causality. Consider the challenge of coordinate systems in astronomy. When we say an object is moving, we mean it is changing position with respect to some reference frame. In cosmology, the standard frame is the comoving frame, which expands with the universe. In this frame, distant galaxies are approximately at rest, and their motion is described by the expansion of space itself. In other frames, such as the frame of the Milky Way or the solar system, these galaxies are moving away at high velocities. The choice of frame affects the description of motion, but not the physical content of observations. Time, too, can be measured in different ways. Coordinate time is the time coordinate in a particular reference frame. Proper time is the time measured by a clock moving along a particular world line. In the presence of strong gravitational fields or high velocities, proper time and coordinate time diverge. An observer far from a black hole might measure years of coordinate time, while an observer near the event horizon experiences only minutes of proper time. This is time dilation, not time reversal. Both observers' clocks tick forward. They simply tick at different rates. Confusion between coordinate systems or failure to account for relativistic effects could produce the appearance of temporal anomalies. Suppose Webb observes a jet of plasma ejected from an active galactic nucleus, a supermassive black hole accreting matter at the center of a distant galaxy. These jets can travel at velocities very close to the speed of light. Due to projection effects and the finite speed of light, components of the jet moving toward us at relativistic speeds can appear to move across the sky faster than the speed of light, a phenomenon known as superluminal motion. This is an illusion. No matter or information is actually traveling faster than light. The geometry is such that the jet component is almost catching up with the light it emitted earlier, compressing the observed time interval. An observer measuring the angular separation between two frames might calculate an apparent transverse velocity greater than the speed of light. If the geometry and orientation of the jet were not correctly determined, this could lead to confused inferences about the trajectory and timing of events. In an extreme case, if multiple components of a jet were observed and their proper motions misidentified, one might construct a scenario where a component appears to be at a location at time t2 that is behind its location at time t1, seemingly moving backward in space. If space and time are conflated in the analysis, this could be misinterpreted as backward time motion. But again, this is a failure of analysis, not a physical reversal. Another source of potential confusion is the interpretation of redshift. Cosmological redshift, the stretching of light due to the expansion of the universe, increases with distance. A galaxy with a redshift of z equals 6 is observed as it was roughly 13 billion years ago when the universe was much younger. The redshift is a direct consequence of the scale factor of the universe increasing over time. However, redshift can also be caused by Doppler motion and gravitational effects. The total observed redshift is a combination of these factors. In principle, peculiar velocities, the motion of an object relative to the smooth expansion of the universe, can add a Doppler component. If an object has a large, peculiar velocity toward us, it might have a smaller redshift than its distance would suggest, or even a net blue shift if it is close enough and moving fast enough. But this does not mean time is running backwards. It means the object's motion has a component toward us. The photons still propagate forward in time. There is, however, a subtlety in how we define now across cosmic distances. In an expanding universe, simultaneity is not absolute. Events that are simultaneous in one frame are not simultaneous in another. There is no unique universal present moment. When we say a distant galaxy is being observed as it was 13 billion years ago, we are using a particular cosmological time coordinate, often chosen to be the proper time measured by co-moving observers. In this framework, the universe has a well-defined age, and we can speak of epochs such as recombination, reionization, and the present day. But this is a convention, a choice of slicing space-time into spatial hypersurfaces of constant time. Other slicings are possible. In one hypothetical slicing, two events that we consider to have different times might be assigned the same time, or vice versa. This freedom does not imply that time can run backwards. It reflects the coordinate nature of time in relativity. Physical predictions, such as the reading on a clock or the spectrum of light measured by a detector, are invariant under coordinate transformations. If Webb observes a spectrum, that spectrum is a physical fact independent of the coordinates used to describe the spacetime in which the observation occurred. To truly assess a claim of matter moving backwards in time, we must scrutinize the data pipeline from photon to published result. Webb's detectors are arrays of pixels, each capable of counting photons. In imaging mode, an exposure consists of integrating the photon counts over a set period, producing a two-dimensional map of brightness across the field of view. In spectroscopic mode, the light is dispersed by wavelength, and the detector records a spectrum for each position in the field. The raw detector output is not immediately usable. It must be calibrated. Calibration corrects for detector artifacts such as dark current, the signal that accumulates even in the absence of light. Flat fielding, which accounts for variations in pixel sensitivity. And cosmic ray hits, high-energy particles that strike the detector and leave bright streaks or spots. Each of these corrections involves algorithms and assumptions. If a cosmic ray hit were not properly identified and removed, it might be mistaken for a real astrophysical signal. If multiple exposures are combined to increase signal to noise, the alignment of the images is critical. A misalignment could cause a source to appear in slightly different positions in different frames, creating the illusion of motion. If the exposures are taken at different times and the misalignment is not corrected, the apparent position change might be misinterpreted as proper motion, or if the time sequence is confused, as motion in an unexpected direction. Pointing stability is another issue. Webb is designed to maintain its pointing with high precision, but it is not perfect. Thermal fluctuations, reaction wheel adjustments, and micrometeorite impacts can introduce small drifts. The fine guidance sensor compensates for these, but residual pointing errors can remain. If an object is observed in multiple visits separated by days or months, and the pointing offset between visits is not accurately known, the reconstructed trajectory of the object could be incorrect. Software that attempts to register images might use field stars as references. But if the field is sparse, or if the stars themselves have proper motion or variability, the registration could introduce errors. In the worst case, these errors might cause an object to appear displaced in a direction opposite to its true motion, or to appear stationary when it is moving, or to jump between frames in a way that defies smooth interpolation. None of these would constitute actual backwards time motion, but they could produce confusing datasets that require careful forensic analysis to interpret correctly. Spectroscopy adds layers of complexity. A spectrum records intensity as a function of wavelength, revealing the physical conditions in the emitting region: temperature, density, composition, velocity, and magnetic fields. Spectral lines can be split, shifted, broadened, or inverted by various processes. Rotational broadening occurs when an object spins, causing one side to be red-shifted and the other blue-shifted, widening the line. Turbulence in a gas cloud produces similar broadening. Doppler shifts from bulk flows move the line center. In a spectrum taken over time, changes in the line profile can indicate changes in velocity. If a line shifts to the blue over successive spectra, it suggests the emitting gas is accelerating toward us. If it shifts to the red, accelerating away. But suppose there is a systematic error in wavelength calibration. Suppose the calibration lamp used to define the wavelength scale has a flaw, or the dispersion solution that maps detector pixels to wavelengths drifts over time. Then the apparent wavelength of a line might shift even if the true velocity is constant. If the shift is in the wrong direction, one might mistakenly infer acceleration when there is none, or even infer a velocity reversal. Spectral line identification is not always straightforward. Astronomical spectra often contain dozens or hundreds of lines from many different elements and ions in various states of excitation. Identifying which line corresponds to which transition requires comparing the observed pattern to laboratory data and theoretical models. In high redshift galaxies, the lines are shifted far from their rest wavelengths, and unfamiliar parts of the spectrum come into view. A line that appears at a particular observed wavelength might be identified as, say, hydrogen alpha redshifted by a certain amount, implying a certain distance and look-back time. But if the line is misidentified, if it is actually a different transition from a different element, or a blend of multiple lines, then the inferred redshift, distance, and velocity will be incorrect. In a time series observation, if line identifications change between spectra, the inferred velocity evolution will be nonsensical. This could lead to reports of objects apparently reversing velocity or exhibiting impossible accelerations, when in fact the problem lies in the line identification. Consider also the phenomenon of light echoes. When a sudden burst of light, such as from a supernova or a stellar flare, illuminates surrounding dust clouds, the reflected light reaches us at a time delay determined by the extra distance the light traveled to the dust and then to us. If the dust is distributed in a complex geometry, different parts of the cloud reflect light at different delays, creating a time-varying pattern of brightness in the dust clouds. The echo can appear to expand outward from the source, even though no matter is actually moving. The speed of this apparent expansion can even exceed the speed of light, as the light-up pattern propagates outward as a geometrical effect, not a physical motion of photons. If the dust geometry were misunderstood, the light echo might be mistaken for an actual outflow of matter, and the timing of the echoes could be confusing. A bright ring of emission might appear to contract rather than expand if the geometry and delays were unusual, creating the appearance of motion inward and possibly, if interpreted carelessly, backwards in time. Variability introduces timing information. If Webb observes a flickering quasar, the light curve, the brightness as a function of time, contains information about the size and structure of the emitting region. By analyzing correlations between brightness at different wavelengths, astronomers can infer how different emission regions respond to changes in the central engine. This technique, called reverberation mapping, has been used to measure the size of black hole accretion disks and the mass of the black holes themselves. The key is that changes in the ultraviolet light from near the black hole are followed, after a time lag, by changes in the optical or infrared emission from gas further out that is responding to the ultraviolet radiation. The time lag corresponds to the light travel time from the inner region to the outer region. If the lags were measured incorrectly, or if the causal relationship were inverted due to a data analysis error, one might conclude that the outer region is responding before the inner region changes, implying a violation of causality. This would be an error, not a true time reversal, but it illustrates how timing measurements must be handled with great care. Transient events add urgency and complexity. Supernovae, gamma-ray bursts, tidal disruption events where a star is torn apart by a black hole. These are dynamic phenomena that evolve over hours to months. Webb can perform target of opportunity observations, interrupting its planned schedule to observe an unexpected transient. The data from these observations are time-sensitive and often released quickly to enable rapid follow-up by other telescopes. But rapid turnaround increases the risk of errors. Calibration might be applied hastily, data quality checks might be cursory, and the interpretation might be preliminary. If a transient appears to behave strangely, brightening when it should be dimming, or showing spectral features that change in an unexpected order, there is pressure to announce a surprising result. Yet the history of astronomy is filled with examples of anomalies that turned out to be instrumental glitches, software bugs, or misinterpretations. The faster the science is done, the higher the risk of such errors. A claim of backwards time motion from a transient observed by Webb would need to withstand intense scrutiny. Independent reanalysis of the data, cross-checks with other wavelengths and other telescopes, and detailed modeling to rule out conventional explanations. Data archives and reproducibility are crucial. Web data are archived at the Mikulski Archive for space telescopes, and the calibration software and reference files are publicly available. In principle, anyone can download the raw data and reprocess it from scratch, checking every step. This transparency is a strength of modern astronomy, but it also means that errors can propagate if the standard calibration pipeline has a flaw. If a bug in the pipeline causes all observations of a certain type to be misprocessed in the same way, then multiple independent reanalyses using the same pipeline would reproduce the same error. Only by using alternative methods or spotting inconsistencies with external data would the error be caught. A claim as extraordinary as time-reversed matter would demand not just reproducibility using the standard pipeline, but validation using entirely independent techniques, different calibration approaches, cross-correlation with data from other instruments on Webb or other telescopes, and theoretical modeling that explains the phenomenon from first principles. The interplay between observation and theory is fundamental. Observations do not interpret themselves. A spectrum is a set of numbers, intensities at wavelengths. To extract physics, we fit models. Blackbody curves for thermal emission, Gaussian profiles for spectral lines, power laws for non-thermal emission, templates for galaxy spectra. Each model embodies assumptions about the underlying processes. If the model is wrong, the inferred physical parameters will be wrong. If an unexpected observation is forced into an inappropriate model, the results can be nonsensical. An example from history. When quasars were first discovered, their high redshifts implied enormous distances and luminosities if the redshift were cosmological. Some astronomers proposed alternative explanations, such as intrinsic redshifts not due to distance, or gravitational redshifts from massive, compact objects. These alternative models made different predictions, and over time, observations ruled them out in favor of the cosmological interpretation. But the process took years and required many independent lines of evidence. A claim of time-reversed matter would similarly require building a coherent model, making testable predictions, and subjecting those predictions to observational tests. What would a model of time-reversed matter look like? In quantum field theory, antiparticles can be interpreted as particles moving backwards in time, as suggested by Feynman's interpretation of positron states. An electron moving forward in time with positive energy is equivalent, mathematically, to a positron moving backward in time with negative energy, where the negative energy and reverse time cancel to give a physically sensible result when boundary conditions are chosen correctly. This is a calculational tool, not a literal statement that antiparticles violate causality. When a positron is created, say in pair production, it moves forward in time like any other particle from the perspective of any observer. Its world line extends from its creation event into the future light cone of that event. The Feynman interpretation is a way of reorganizing the mathematics of quantum field theory to avoid negative energy states, but it does not imply that we could detect a positron and conclude that time is running backwards. There are also interpretations of quantum mechanics that involve retrocausality, where future boundary conditions influence past events. The transactional interpretation, proposed by John Cramer, it describes quantum measurements as transactions between emitter and absorber, with advanced waves traveling backward in time from absorber to emitter, and retarded waves traveling forward, forming a handshake across time. The two-state vector formalism and weak measurements explore how post-selected ensembles can exhibit unusual statistical properties that seem to involve backward influence. These are highly controversial and not part of the standard Copenhagen or many worlds interpretations of quantum mechanics. Even in these interpretations, causality at the macroscopic level is not violated. The retrocausal influences are subtle and do not allow signaling information backward in time or decreasing entropy. For Webb to observe time-reversed matter in a retrocausal framework, one would need a macroscopic, reproducible phenomenon that could be unambiguously linked to such effects, which remains purely speculative. Let us explore another potential mechanism: topological defects in spacetime. In the early universe, as it cooled and underwent phase transitions, defects might have formed: cosmic strings, domain walls, or monopoles. Some theories suggest these defects could have exotic properties, including effects on the causal structure nearby. A cosmic string, for example, is a one-dimensional object with immense tension. Space-time around a cosmic string is conical. If you circle around the string, you return to a point slightly displaced from where you started, as if a wedge of space were removed. Light passing near a cosmic string can be lensed, producing double images of background objects. In more extreme speculative scenarios, a spinning cosmic string or other defect might allow closed time-like curves in its vicinity. If such a defect existed and Webb happened to observe matter near it, there might be signatures of unusual causal structure. But cosmic strings have not been detected, and their existence is constrained by observations of the cosmic microwave background and the large-scale structure of the universe. Observing time-reversed motion via a cosmic string would first require discovering a cosmic string, an extraordinary find in itself, and then demonstrating that the observed behavior could not be explained without invoking closed time-like curves, an even higher bar. Wormholes represent another class of exotic solutions. A traversable wormhole, if it could be stabilized with exotic matter, would connect two regions of spacetime, potentially separated by vast distances or even times. Light or matter entering one mouth of the wormhole would emerge from the other mouth. If the two mouths were at different times in some reference frame, the wormhole would enable time travel. Morris and Thorne explored such solutions in the 1980s, showing that while they satisfy Einstein's equations, they require matter that violates energy conditions. No such matter is known to exist, and quantum field theory in curved spacetime suggests that attempts to create such configurations would be unstable or lead to singularities. Even if a wormhole existed, observing it with Webb would be extraordinarily difficult. The wormhole mouths might be microscopic, or if macroscopic, they might be indistinguishable from black holes unless matter or light were seen to traverse them. And even then, proving that traversal involved time travel rather than just spatial displacement would require synchronized clocks on both sides and careful measurement of the timing of signals passing through, well beyond Webb's capabilities. Let us return to the practical. What signatures in Webb data could conceivably be interpreted, even mistakenly, as matter moving backwards in time? One scenario involves microlensing. When a compact massive object, such as a star or black hole, passes in front of a background source, the gravitational lensing magnifies the source's light, causing a temporary brightening. The light curve has a characteristic shape, symmetric if the alignment is perfect, asymmetric if not. Microlensing events typically last days to months. If the background source is itself variable, the microlensing magnification can create complex light curves where different parts of the source are magnified at different times. In an extreme case, if the source has structure and the microlensing caustic, the curve of infinite magnification in the source plane crosses the source in a particular way. Different regions might brighten in an order that seems counterintuitive. Moreover, if the source is strongly lensed into multiple images, each image can experience microlensing independently, leading to uncorrelated brightness variations. An astronomer monitoring these images might see one image brighten, then another, and if the lensing geometry were not understood, might infer a physically impossible sequence of events. Another scenario involves time domain astronomy and the cadence of observations. Suppose Webb observes a target 3 times at T1, T2, and T3. At T1, a feature is present. At T2, it is absent. At T3, it is present again. If the feature is a transient phenomenon, its reappearance might seem strange, but there are many explanations. It could be a periodic phenomenon, a recurrent transient, or two separate events coincidentally at the same location. However, if the analysis assumes the feature should evolve monotonically, say an expanding shell of gas that should only grow, not shrink, then its reappearance at the same size might be interpreted as impossible, possibly suggesting that between T2 and T3, time ran backwards and the shell returned to an earlier state. This interpretation would be incorrect. The assumption of monotonic evolution might be wrong. Perhaps the shell is oscillating, or there are two shells overlapping, or the shell has a clumpy structure that changes its appearance as it rotates or as density enhancements move through it. Projection effects are insidious. A three-dimensional structure projected onto a two-dimensional image can create misleading impressions of motion. A spiral arm in a galaxy might appear to wind more tightly or unwind depending on the viewing angle. A jet seen from the side might show components that appear to move laterally across the jet, while the same components viewed from a different angle might appear to move forward or backward along the jet axis. If the orientation of the object changes over time, say due to precession, the projected motion can be complex and counterintuitive. An observer unaware of the changing orientation might infer motion in the plane of the sky that is not representative of the true three-dimensional velocity. In an extreme case, a component might appear to move in a direction opposite to its true motion due to the projection. Rotation can create apparent motion that is not translational. Consider a rotating disk of gas around a black hole. As the disk rotates, hotspots or density waves within the disk move in circular orbits. Viewed from above, the motion is clearly circular. Viewed edge-on, the hotspots move back and forth along the line of sight, producing periodic Doppler shifts. Red shift when moving away, blue shift when moving toward. If the disk is viewed at an intermediate angle and observed at discrete times, the hot spot's positions will shift in the image plane in a pattern that reflects the rotation. If the rotation period and the observation cadence are such that the hot spots appear at positions that are not in simple sequence, an unwary analyst might construct a motion vector that seems to reverse direction. This is a stroboscopic effect, similar to the wagon wheel effect in films where spinning wheels appear to rotate slowly backwards when the frame rate and rotation rate interact. Pattern speeds versus material speeds present another subtlety. In some systems, such as spiral galaxies, the spiral arms are not material structures that rotate as solid bodies. Instead, they are density waves, regions where stars and gas are temporarily compressed as they orbit. The density wave rotates at a pattern speed that can differ from the orbital speed of the material. Stars enter a spiral arm, slow down as they pass through the overdensity, and then exit on the other side, while the arm itself rotates at the pattern speed. An observer measuring the motion of a bright feature in the arm might see it move at the pattern speed, even though the individual stars are moving at different speeds. If the pattern speed and the material speed are confused, the inferred dynamics will be incorrect. In principle, a density wave could have a pattern speed that is retrograde relative to the rotation of the disk, making the spiral pattern appear to rotate backwards, even though the stars orbit forward. This is a kinematic illusion, not a violation of time's arrow. Phase delays in multi-wavelength observations can also create confusion. Suppose a region emits light at multiple wavelengths, but the emission at different wavelengths originates from different physical processes or locations with different light travel times. For instance, in a pulsar, radio emission might come from high in the magnetosphere, while X-rays come from near the surface. The light travel time difference is tiny, but in a rapidly rotating neutron star, this can translate to a phase offset in the pulsations observed at different wavelengths. If the radio pulse appears to arrive after the X-ray pulse in a way that contradicts the assumed geometry, one might be tempted to invoke exotic explanations. More likely, the geometry or emission mechanism is not as assumed. Recombination and fluorescence introduce delays between excitation and emission. When a gas cloud is ionized by ultraviolet radiation, the recombination of electrons and ions produces emission lines such as hydrogen alpha. This emission does not happen instantaneously. There is a delay corresponding to the recombination time and the light travel time across the cloud. If the ionizing source varies, the recombination emission will vary in response, but with a lag. The lag depends on the density of the gas, the distance from the ionizing source, and the recombination rate. By measuring the lag in different lines, astronomers can map the structure of the emitting region. But if the lags are measured incorrectly, or if the assumptions about the geometry are wrong, the inferred structure can be nonsensical. One might calculate that a region is responding before it is illuminated, seemingly violating causality. The error would lie in the modeling, not in physics. Now consider the broader implications if the claim were taken at face value. Suppose, for the sake of argument, that Webb truly observed matter moving backwards in time, and all conventional explanations had been exhaustively ruled out. What would this mean for physics? First, it would imply a breakdown of the second law of thermodynamics, at least locally. The matter would need to be decreasing in entropy, spontaneously becoming more ordered. This is not forbidden by the microscopic laws of physics, which are time reversal invariant in many cases, but it is overwhelmingly improbable. The probability of a macroscopic entropy decrease is exponentially suppressed, proportional to the exponential of minus the entropy change divided by Boltzmann's constant. For a system of many particles, this probability is vanishingly small. Observing such a decrease would be like watching a video of a broken cup reassembling itself and leaping onto the table. It is not impossible in principle, but the universe would need to be vastly older than it is for such an event to happen, by chance even once. Therefore, if observed, it would suggest not a statistical fluctuation, but a new physical principle or a modification of known laws. Second, it would challenge the causal structure of spacetime. If matter is moving backwards in time, then there must be a way for it to influence events in its own past, creating the potential for paradoxes. The grandfather paradox, in which a time traveler prevents their own birth, is the classic example. In physics, such paradoxes are avoided if closed time-like curves do not exist, or if consistency conditions prevent paradoxical actions. Novikov's self-consistency principle asserts that even if closed time-like curves exist, only self-consistent solutions are realized. You cannot change the past because your actions are already part of the past. This principle does not resolve all conceptual issues, and it is unclear whether it can be derived from deeper principles or whether it is an additional postulate. If Webb observed time-reversed matter, we would need a consistent theoretical framework to accommodate it, which might involve rethinking causality or accepting that our observations are part of a self-consistent loop that we do not yet understand. Third, it would have implications for quantum mechanics and the nature of time. Quantum field theory treats particles and antiparticles on an equal footing and incorporates both advanced and retarded propagators in its formalism. The Feynman path integral sums over all possible histories, including those that might seem to involve backward time evolution. But the boundary conditions and the integration measure ensure that the result respects causality. If a macroscopic system were observed to evolve backwards in time, it might hint at new quantum effects at large scales, or at an interaction between the quantum vacuum and spacetime curvature that permits retrocausal correlations. This would be Nobel Prize level physics, overturning a century of understanding. It would demand new mathematics, new experiments, and a new philosophical framework for understanding the nature of reality. Yet, the history of science is not filled with examples of such overturns from single observations. More often, anomalies are resolved by better understanding of the instruments, the data, or the models. The faster-than-light neutrinos reported by the Opera experiment in 2011 turned out to be due to a faulty cable connection and a miscalibrated clock. The cosmic microwave background cold spot, once speculated to be a portal to another universe or a sign of exotic physics, is now understood as a statistical fluctuation and possibly a foreground effect. The anomalous acceleration of the Pioneer spacecraft, which inspired proposals of new physics, was ultimately explained by anisotropic thermal radiation from the spacecraft itself. Each of these cases involved careful measurement, extensive analysis, and ultimately a mundane explanation that restored confidence in established physics. The claim of time-reversed matter would undergo a similar process. Every possible source of error would be examined. Detector behavior, calibration, cosmic rays, scattered light, pointing errors, timing offsets, software bugs, and human error in the analysis. Only after all of these were ruled out with high confidence would the community begin to seriously consider that the laws of physics as understood are incomplete. Webb's design and operation are the result of decades of engineering and planning. Every aspect of the telescope has been tested and characterized. The mirrors were polished to nanometer precision and aligned in space using actuators. The instruments were calibrated using standard stars and lamps before launch and are monitored continuously using onboard calibration sources. The detectors, based on mercury-cadmium telluride arrays for the infrared, have been studied for their noise properties, linearity, and stability. The electronics and data handling systems have redundancy and error checking. The ground system that receives the data, stores it, and processes it through the calibration pipeline has been validated against simulations and test data. All of this infrastructure is designed to ensure that the data Webb produces are accurate and reliable. An anomalous result from Webb would first be checked against this infrastructure. Did the anomaly appear in multiple detectors, in multiple filters, in multiple observing modes? Is it reproducible? Does it appear in other targets or only in one? Suppose the anomaly were specific to a single target. That would be suspicious. Instrumental effects usually affect all observations in a similar mode, not just one object. A single object anomaly suggests either something unique about that object or a coincidence of timing, such as a cosmic ray hit or a micrometeorite impact during that specific observation. If the anomaly appeared in multiple targets, that would be more concerning, suggesting a systematic issue with the instrument or pipeline. But it would still point toward an instrumental cause rather than a revolution in physics. If the anomaly were seen by multiple instruments on Webb, or by Webb and other telescopes, the case would strengthen. Cross-validation with Hubble, Chandra, the Atacama Large Millimeter Array, or ground-based observatories would be essential. Each telescope has different systematics, and an astrophysical phenomenon should appear consistently across platforms, while an artifact would not. The role of the astronomical community in vetting such a claim cannot be overstated. Peer review, replication, and public skepticism are the immune system of science. When a surprising result is announced, other groups request the data, reanalyze it, and attempt to reproduce or refute the finding. Conferences are held, papers are written, and debates occur. This process can take months or years. During this time, the initial excitement may fade as prosaic explanations emerge, or the result may solidify as more evidence accumulates. The detection of gravitational waves by LIGO in 2015 is an example of a surprising result that withstood scrutiny. The signal was seen by two detectors simultaneously, with the time delay and waveform consistent with a pair of merging black holes. The detectors had been exquisitely calibrated, and extensive work had been done to rule out environmental noise and instrumental artifacts. The discovery was announced only after months of internal review, and after ruling out a vast array of potential false positives. Even then, some skeptics questioned the result, but subsequent detections, including one with an optical counterpart, confirmed that gravitational waves are real and detectable. A claim of time-reversed matter would need to meet an even higher standard, given how extraordinary it is. Let us delve deeper into the nature of time itself. In Newtonian mechanics, time is absolute and universal, ticking uniformly everywhere. In special relativity, time is relative. Different observers in relative motion measure different time intervals between the same events. In general relativity, time is further entwined with space and gravity. Time dilation occurs near massive objects. Clocks run slower in stronger gravitational fields. This has been confirmed by precise measurements with atomic clocks on Earth and in orbit. The global positioning system depends on relativistic corrections, without accounting for both special and general relativistic time dilation. GPS coordinates would drift by kilometers per day. Despite these relativistic effects, time still flows forward for all observers. A clock may tick faster or slower, but it never ticks backward. The world line of a massive particle, the trajectory it traces through spacetime, always has a time-like tangent vector pointing toward the future. Time-like, space-like, and null are the three types of intervals in spacetime. A time-like interval connects events that can be causally related, where a signal traveling slower than light can pass from one to the other. A space-like interval connects events that cannot be causally related, separated by too much space and too little time for even light to traverse. A null interval is the path of light itself. The distinction is preserved under Lorentz transformations. You cannot boost to a frame where a time-like interval becomes space-like. This structure underpins causality. For matter to move backwards in time, its world line would need to curve back on itself, forming a closed time-like curve. Near such a curve, causal structure would break down. Effects could precede causes, and self-consistency conditions would become paramount. Whether nature permits this is an open question, but most physicists suspect that quantum gravity effects, whatever they may be, prohibit closed time-like curves, preserving causality even in the most extreme environments. String theory, loop quantum gravity, and other approaches to quantum gravity attempt to unify general relativity and quantum mechanics. In these theories, space-time itself may not be fundamental, but emergent from deeper structures: strings, branes, spin networks, or quantum information. At the Planck scale, approximately 10 to the minus 35 meters, space-time may be granular or have a different topology than the smooth manifold of classical relativity. Time may not be a continuous parameter, but a discrete or approximate concept. These ideas are speculative and lack experimental confirmation, but they raise the possibility that the nature of time could be more exotic than currently understood. Even so, the macroscopic arrow of time, the distinction between past and future, is expected to emerge from the statistical behavior of quantum degrees of freedom, much as it does in classical thermodynamics. Observing macroscopic time reversal would not only challenge relativity, but also require a new understanding of how the microscopic quantum world gives rise to the classical thermodynamic world. The arrow of time has several manifestations. The thermodynamic arrow points from low entropy to high. The cosmological arrow points from the Big Bang toward an expanding, cooling universe. The radiative arrow points from sources emitting radiation to the future light cone, not the past. The psychological arrow, our subjective sense of time passing, correlates with memory formation, which is a thermodynamic process of encoding information, increasing entropy. The quantum arrow, in the collapse interpretation, points from superposition to definite measurement outcome, a process that appears irreversible. All of these arrows align in our experience, but in principle, they could point in different directions. If Webb observed matter moving backwards in time, one would need to ask, which arrow is reversed? If only the thermodynamic arrow is reversed locally, entropy decreases while everything else proceeds normally. If the causal arrow is reversed, effects precede causes. If the quantum arrow is reversed, measurements uncollapse and systems return to superpositions. Each scenario has different implications and challenges. Let us consider a concrete hypothetical. Suppose Webb observes a supernova in a distant galaxy, and the light curve shows an unusual pattern. The brightness increases for several days, then decreases, then increases again to the same peak, then decreases in exactly the reverse sequence, as if the explosion is rewinding. The spectrum during the rise shows the characteristic features of a Type 1, a supernova: silicon, sulfur, iron, expanding at thousands of kilometers per second. During the reversed phase, The spectrum shows the same lines, but the Doppler shift decreases, suggesting the ejecta are slowing down and reversing, falling back toward the explosion center. If taken literally, this would imply entropy is decreasing. The ejecta are reconverging. The thermal energy is being converted back to gravitational potential, and the system is returning to its pre-explosion state. This blatantly violates the second law of thermodynamics. Before accepting this conclusion, every alternative must be explored. Could this be a light echo? If the supernova explosion illuminated a nearby dust shell, the reflected light could create a delayed, reversed brightness pattern. The shell would need a very specific geometry, a parabolic or elliptical reflector with the supernova at the focus, such that light traveling outward and reflecting off the shell converges back toward the observer. The geometry seems unlikely, but is not impossible. The spectrum of the echo would be similar to the direct light, redshifted by the same amount, but the echo would be polarized by the dust scattering, and its brightness profile would depend on the dust distribution. Observations in polarized light and detailed modeling could test this hypothesis. If the polarization and spatial distribution are inconsistent with a light echo, the hypothesis is ruled out. Could this be a lensing effect? If a massive object is moving between us and the supernova, the lensing magnification could change over time, modulating the observed brightness. If the lens moves in just the right way, the magnification could increase, then decrease, then increase again, mimicking a reversed light curve. However, lensing is achromatic. It affects all wavelengths equally. If the reversed brightness is seen in one filter but not another, lensing is ruled out. Also, lensing does not affect the spectrum's Doppler shift. If the ejecta truly appear to be slowing and reversing, lensing cannot explain that. A more exotic lensing scenario involves a binary lens, or a lens with complex mass distribution that creates multiple images with different time delays. If the time delays conspire to make the images brighten in a reversed sequence, the combined light curve could appear reversed. This requires a very specific, fine-tuned lens geometry. Observations at higher angular resolution or at multiple epochs could resolve the multiple images and test this scenario. Could this be an intrinsic physical process? Perhaps the supernova is not a standard Type 1a, but a new type of transient with unusual dynamics. Could a star explode, then somehow re-implode? In known physics, this does not happen. Once a star explodes, the ejecta have kinetic energy that carries them outward. For them to reverse and fall back, they would need to lose that energy or be decelerated by an external force. Gravitational infall could decelerate the ejecta if there is a sufficiently massive object nearby. But this would require a black hole or neutron star at the explosion site, and the deceleration would not be symmetric. The ejecta would not rewind the explosion. Another possibility is that the explosion was not a single event, but a series of pulses, with each pulse creating a similar light curve. If the pulses are timed right, the combined light curve could appear to rise, fall, rise again, and fall again. The spectrum would need to show multiple velocity components corresponding to the different pulses, which could be tested observationally. Could this be a data artifact? Perhaps the observation was interrupted, and the data were assembled incorrectly, placing later observations before earlier ones. This is a trivial error that would be caught by checking the timestamps in the data headers. If the timestamps are correct and in sequence, this explanation is ruled out. Could the detector have saturated, causing nonlinear response and distorting the light curve? Saturation typically causes the measured brightness to be lower than the true brightness, not to reverse in time. Could there be a software bug in the photometry pipeline that miscalculates the brightness? This could be checked by reprocessing the data with independent software. Could the target have been misidentified and the light curve actually shows two different objects? This could be checked by examining the coordinates and ensuring the same source is measured in all frames. After ruling out all these possibilities, if the observation still appears to show time-reversed behavior, the next step is to make predictions and test them. If the supernova ejecta are truly reversing in time, then the ejecta should eventually reconverge to the point of explosion and the star should return to its pre-explosion state. Continued monitoring over weeks or months should show this process completing. If the light curve simply freezes or does something unexpected after the initial reversed phase, that would be inconsistent with a simple time reversal and would suggest a more complex process. If the process completes and the object disappears, leaving no remnant, that would be extraordinary evidence. It would also raise the question, where did the energy go? The explosion released a tremendous amount of energy, more than the sun emits in its entire lifetime. If that energy is somehow removed from the universe or returned to a potential form without radiating away, it would violate energy conservation unless there is an unseen energy sink or exotic physics at play. Another test. Look for the initial explosion. If the supernova is reversing in time, there should be an earlier phase where it exploded normally. Archival data from surveys that monitor the sky for transients could reveal the initial rise. If the initial rise is absent, that would suggest the object never exploded in the usual sense, and the observed reversed curve is something entirely different. If the initial rise is present and the light curve shows explosion followed by implosion, the total duration of the event would be unusually long, and the energetics would be puzzling. The time-reversed phase should release as much energy as the explosion absorbed. But where does that energy come from? Suppose, for the sake of pushing the scenario further, that all tests are passed. The object is confirmed to be a single supernova. The light curve and spectrum unambiguously show forward explosion, followed by reversed implosion. The energetics are consistent if one allows for a time-reversed thermodynamic process. What then? The implications are staggering. First, the local patch of spacetime around the supernova must permit closed time-like curves or some other mechanism for matter to reverse its temporal trajectory. This would require exotic matter or energy, far beyond anything in the standard model of particle physics. Second, the rest of the universe continues forward in time, so there must be a boundary or interface between the time-reversed region and the normal region. How does this boundary work? How is causality preserved across it? Third, if such an event can happen once, can it happen again? Is it a rare fluctuation, or is there some process that generates time-reversed regions? Are there observable precursors or signatures that would allow prediction? The theoretical framework to accommodate this would need to be constructed. Perhaps a new field or particle mediates the time reversal, coupling to matter in a way that allows entropy to decrease locally by transferring entropy elsewhere, to a hidden sector or another brane in a higher dimensional space. Perhaps the time reversal is an illusion created by a higher dimensional process. What appears as matter moving backwards in time in our four-dimensional spacetime is actually matter moving forward in a five-dimensional bulk along a trajectory that projects onto our spacetime in a reversed manner. These are speculative ideas that have been explored in the context of cosmology and high energy physics, but turning them into concrete, testable models is a formidable challenge. The philosophical implications are equally profound. If time can run backwards for matter, what does that mean for free will, for the nature of causality, for the meaning of past and future? Our language, our thought processes, our very cognition are structured around the unidirectional flow of time. We remember the past and anticipate the future, not the reverse. If a physical system can reverse, does it experience the reversal? Is there a subjective perspective from within the time reversed matter? And if so, what does it perceive? These questions venture into philosophy of mind and metaphysics, areas where physics provides limited guidance. Returning to the grounded analysis, the overwhelming likelihood is that any report of Webb capturing matter moving backwards in time would be the result of a misunderstanding, a misinterpretation, or an instrumental artifact. The robustness of known physics, the extensive testing of Webb's instruments, and the historical track record of anomalies being resolved conventionally all point in this direction. However, the possibility, however remote, that the observation is genuine and represents new physics cannot be dismissed without investigation. Science progresses by taking surprising observations seriously, testing them rigorously, and following the evidence wherever it leads. If Webb has indeed captured something extraordinary, the data will withstand scrutiny and additional observations will corroborate it. If not, the investigation itself will deepen our understanding of the instruments, the astrophysics of the observed object, and the subtleties of data analysis. Let us examine the claim from yet another angle: the semantics of captured. In common usage, capturing something means recording it, preserving a moment. A photograph captures a scene. A video captures motion. Webb captures light from distant objects, and from that light, information about the objects is extracted. But light itself always travels forward in time from emission to detection. The photons that strike Webb's detectors today were emitted by distant objects in the past, and they propagated through space at the speed of light, arriving in the forward time sequence. Even if the source object is doing something unusual, the light reaching us encodes that behavior in a forward temporal record. The sequence of photon arrivals is ordered. Photons from earlier events arrive earlier. Photons from later events arrive later. Modulo light travel time and geometric delays. If the object is at a fixed distance and emitting continuously, the light we receive traces the history of the object in forward time. But what if the object is not at a fixed distance? What if it is moving toward us at relativistic speed? The light emitted later in the object's history could reach us sooner than light emitted earlier if the object is catching up with its own light. This creates a time compression effect. An event that takes hours in the object's rest frame might be observed to occur over minutes because the object is moving toward us and reducing the light travel distance as it emits. In the extreme case of a source moving directly toward us at nearly the speed of light, the observed duration of an event could be much shorter than the actual duration. Conversely, a source moving away would have its light time-dilated and redshifted, stretching the observed duration. These are Doppler and relativistic beaming effects, well understood and observed in astrophysical jets and gamma-ray bursts. They do not constitute time reversal, but do complicate the relationship between observed light curves and intrinsic source behavior. If Webb observes a source that is both varying intrinsically and moving with a complex velocity, disentangling the intrinsic variations from the motion induced effects requires modeling. The model would include the source's rest frame light curve, its velocity as a function of time, the geometry of its motion relative to our line of sight, and relativistic corrections. If the model is misapplied or if the wrong assumptions are made, the inferred rest frame behavior could be incorrect, potentially leading to nonsensical conclusions, such as reversed time evolution. The check is to test the model against multiple wavelengths, multiple epochs, and physical consistency. A correct model should explain all the data with a single set of parameters and should make predictions that can be verified. Consider also the role of selection effects and publication bias. Astronomers observe thousands of objects, and most of them behave as expected. Occasionally, an object behaves unusually, and that unusual behavior attracts attention. Papers are written, press releases are issued. The unusual case is highlighted, while the thousands of normal cases are relegated to catalogs. This creates a bias. We hear about the anomalies, not the regularities. Some anomalies are genuinely new phenomena. Pulsars, quasars, gamma ray bursts were all anomalies when first discovered, but many turn out to be statistical flukes, rare but not impossible events in a large sample, or misinterpretations. If one observes 10,000 transients, the most extreme outlier in the sample might be 5 sigma away from the mean, which sounds significant. But with a large enough sample, 5 sigma events happen by chance. The key is replication. Does the phenomenon appear in multiple independent observations? If a single Webb observation appears to show time-reversed motion, the correct response is not to immediately publish a revolutionary claim, but to seek additional observations. Observe the target again. Observe similar targets. Compare with archival data. Consult with experts in data analysis, instrumentation, and theoretical astrophysics. Present the finding at conferences and solicit feedback. Only after extensive vetting, if the phenomenon remains unexplained by conventional means and is reproducible, would it be appropriate to propose an exotic explanation and frame it as a hypothesis to be tested. The claim, James Webb just captured matter, moving backwards in time as a headline is almost certainly premature, sensationalized, or based on a misunderstanding. As a hypothesis to be investigated, it is legitimate. As a confirmed discovery, it would require far more evidence than currently plausible. Let us explore the observational techniques Webb uses in more detail to understand how temporal information is encoded in its data. Webb's instruments can operate in several modes. Imaging mode produces pictures, two-dimensional arrays of brightness values at specific wavelengths selected by filters. Each image is an integration over the exposure time, typically hundreds to thousands of seconds. If the target is steady, multiple exposures can be combined to increase signal to noise. If the target is variable, each exposure is a snapshot, and comparing exposures taken at different times reveals the variability. The time resolution is limited by the exposure time. Variations faster than the exposure time are blurred. For most astronomical sources, this is not a limitation because intrinsic variations are slow. But for some targets, such as pulsars or flickering black hole systems, faster time resolution is needed. Webb's detectors can be read out more rapidly for time series observations. By taking many short exposures in succession, a light curve can be constructed with time resolution of seconds or even sub-seconds, limited by the detector readout time and data rate. This mode is used for observing transiting exoplanets, where the planet passes in front of its star and causes a brief dimming, or for observing transient events. The timestamps of each exposure are recorded with precision reference to coordinated universal time, allowing comparison with observations from other telescopes. If a light curve shows unusual behavior, such as a dip followed by a rise that defies the expected exponential or power law form, astronomers would fit models to the data to understand the source. Models might include eclipses, pulsations, accretion disk instabilities, or lensing. An unusual light curve alone does not imply time reversal. It implies unusual physics or geometry that must be identified. Spectroscopy provides a different kind of time information. A spectrum taken at a single epoch shows the instantaneous, integrated over the exposure, state of the source's emission. By repeating the spectrum over time, changes in the spectral features can be tracked. For instance, if a spectral line shifts in wavelength from one spectrum to the next, it indicates a change in velocity. If the line's flux increases, it indicates increased emission in that transition, possibly due to changes in temperature, density, or excitation. Time-resolved spectroscopy is powerful for diagnosing dynamics, winds, jets, rotating disks, infalling or outflowing gas. The interpretation depends on understanding the physics of the emission. If a line shifts to the blue over time, the gas is accelerating toward us or decelerating away from us. If the shift is to the red, the opposite. If the shift reverses, the gas is oscillating or the geometry is changing. None of this necessarily implies backward time flow. It can all be explained by three-dimensional motion and viewing geometry. Webb's spectroscopic modes include multi-object spectroscopy, where many sources in the field are observed simultaneously using a micro-shutter array, and integral field spectroscopy, where every pixel in a small field of view gets a spectrum, producing a three-dimensional data cube, two spatial dimensions, and one spectral dimension. Analyzing these data cubes allows mapping of velocity fields across extended objects like galaxies. The velocity at each location can be measured from the Doppler shift of emission lines. In a rotating disk galaxy, one side is approaching and blue shifted, the other side receding and red shifted, producing a characteristic velocity pattern. If the pattern is distorted, it might indicate non-circular motions, such as a bar, spiral arms, or inflow/outflow. A truly bizarre velocity pattern, where adjacent regions have velocities that seem causally disconnected or time reversed, would prompt careful checking of the data reduction. Are the wavelengths calibrated correctly? Are the line identifications correct? Are there multiple velocity components blended in the line profile? One must also consider the impact of cosmic expansion on observed velocities. Galaxies are embedded in the expanding universe, and their recession velocities are a combination of the cosmological Hubble flow and their peculiar velocities. At high redshift, the Hubble flow dominates, and galaxies are receding at substantial fractions of the speed of light. The redshift is then primarily cosmological. At low redshift, peculiar velocities can be significant. The local group of galaxies, including the Milky Way and Andromeda, is part of larger structures like the Virgo supercluster and is being pulled toward the Great Attractor and the Shapley supercluster. These motions produce Doppler shifts that combine with the Hubble flow. A galaxy that is being pulled toward us by gravitational attraction might have a smaller redshift than its distance would suggest, or even a blue shift. Andromeda, for instance, is approaching the Milky Way and is blue shifted. This is normal dynamics in an expanding universe, not time reversal. If a distant galaxy were observed to have a blue shift much larger than expected, it might indicate a very high peculiar velocity toward us, perhaps due to an extremely massive nearby attractor, or it might indicate a measurement error. If the blue shift were so large that it could not be explained by any plausible peculiar velocity approaching the speed of light, one would suspect a problem with the redshift measurement or a misidentification of the spectral lines. Quasars and active galactic nuclei can have broad emission lines due to gas moving at thousands of kilometers per second in the vicinity of the black hole. These lines can be blue shifted or red shifted depending on which part of the flow is dominating the emission. Misidentifying a blue shifted broadline component as the systemic redshift of the galaxy would lead to an incorrect distance and incorrect interpretation of the velocity. Now let us turn to the cutting edge of theoretical physics and consider whether any plausible, if speculative mechanisms could give rise to observable signatures that might be misinterpreted as matter moving backwards in time. One area is quantum field theory in curved spacetime, particularly near black holes. The event horizon of a black hole is a null surface, the boundary beyond which nothing can escape. According to an external observer, an object falling toward the horizon appears to slow down and freeze at the horizon, its light increasingly redshifted. Time dilation becomes infinite at the horizon. From the perspective of the infalling observer, however, nothing special happens at the horizon. They cross it in finite, proper time. This discrepancy between perspectives is a consequence of the extreme curvature and the choice of coordinates. If Webb were to observe matter falling into a black hole, the observed light would show the matter approaching the horizon and appearing to stop, with its light fading and redshifting. This is a forward time process from all perspectives, though the relationship between coordinate time and proper time is unusual. Hawking radiation introduces another subtlety. Quantum effects near the horizon cause the black hole to emit thermal radiation, slowly losing mass. The radiation arises from particle-antiparticle pairs, created near the horizon, with one particle falling in and the other escaping. From the outside, the escaping particle appears as radiation. Hawking's original calculation used a mode decomposition in which particles are defined relative to the vacuum state far from the black hole. The outgoing radiation is entangled with the ingoing particles, leading to the black hole information paradox. Some interpretations and proposed resolutions of the paradox involve non-local effects or complementarity, where different observers describe the physics using different but complementary frameworks. None of this involves matter moving backwards in time, but the quantum information and entanglement aspects are subtle and still debated. If Webb could observe a black hole accreting matter and emitting Hawking radiation, which is not currently feasible, as Hawking radiation is incredibly faint for stellar mass or supermassive black holes, the signatures would be thermal emission and possible correlations between infalling and outgoing particles. There is no prediction of matter emerging from the black hole in a time-reversed state. Even in scenarios involving black hole evaporation and information recovery, the information comes out encoded in the radiation in a highly scrambled form, not as matter literally reversing its trajectory. Wormholes and traversable spacetimes offer another speculative avenue. If a wormhole connects two regions of spacetime, and if one mouth of the wormhole is moving relative to the other, or is in a different gravitational potential, time dilation could make one mouth older than the other. A signal entering one mouth and exiting the other might emerge at a time that is earlier than expected, or even earlier than the entry in some coordinate systems, creating the possibility of closed time-like curves. This is the basis of time machine proposals using wormholes. The critical issue is stability. Holding a wormhole open requires exotic matter with negative energy density, and attempts to create such configurations might lead to instability or singularities. Even if a wormhole could be observed, the observational signatures would likely involve lensing effects and possibly accretion flows, not clear evidence of time travel. Advanced civilizations, if they exist and have mastered exotic physics, might conceivably create structures or phenomena that involve manipulated space-time geometry or time loops. Observing the signature of such technology would be an extraordinary finding in its own right, often discussed under the umbrella of technosignatures or SETI, search for extraterrestrial intelligence. A time-reversed process could be an artificial phenomenon rather than a natural one. However, invoking advanced civilizations is a hypothesis of last resort, to be considered only after all natural explanations have been exhausted and the evidence is incontrovertible. The principle of Occam's razor favors simpler explanations, and the simpler explanation for an anomalous observation is almost always instrumental or astrophysical, not technological or exotic physical. Let us examine the role of simulations and models in interpreting Webb data. Modern astrophysics relies heavily on simulations, hydrodynamic simulations of galaxy formation, radiative transfer simulations of light propagating through dusty media, N-body simulations of gravitational dynamics. These simulations are run forward in time, starting from initial conditions and evolving the system according to the laws of physics. The output is a synthetic universe that can be compared to observations. If a simulation produces a feature similar to what Webb observes, that strengthens the interpretation. If no simulation can reproduce the feature, it suggests either that the physics in the simulation is incomplete or that the observation is not what it seems. Time-reverse dynamics are not included in standard simulations because they are not part of standard physics. To simulate time-reversed matter, one would need to impose it as an initial condition or modify the equations of motion, which would be an ad hoc and unmotivated choice, unless there is a theoretical reason to do so. Machine learning and artificial intelligence are increasingly used in astronomy for tasks such as classifying objects, detecting anomalies, and searching for patterns in large datasets. A neural network trained on millions of galaxies can learn to recognize spiral structure, mergers, and other features. If fed an image of something truly unusual, the network might flag it as an anomaly. However, the network is only as good as its training data. If the training data contain no examples of time-reversed matter, because it has never been observed, the network cannot reliably identify it. The network might flag the object as anomalous, but human experts would still need to interpret what the anomaly represents. Machine learning is a powerful tool for sifting through data, but it does not replace physical understanding and critical analysis. The culture of modern astrophysics, with its emphasis on reproducibility, open data, and collaborative verification, provides a strong safeguard against false claims. Data from major observatories like Webb are public after a proprietary period, allowing anyone to analyze them. Software tools for data reduction and analysis are often open source. Papers undergo peer review, where experts in the field scrutinize the methods and conclusions. Even after publication, other researchers can challenge the findings. This ecosystem of checks and balances makes it difficult for incorrect or sensational claims to stand for long. A claim as extraordinary as time reversed matter would be subjected to intense scrutiny from the community. Every step of the analysis would be questioned, alternative explanations would be proposed, and independent analyses would be performed. The claim would only gain acceptance if it survived all of these challenges. Historical precedents offer guidance. When pulsars were first discovered in 1967 by Jocelyn Bell and Anthony Hewish, the regular radio pulses were so unexpected that they were jokingly labeled LGM1 for little green men, as a nod to the possibility of an artificial signal. Careful analysis showed that the pulses were natural, originating from rotating neutron stars with intense magnetic fields. The discovery was revolutionary but fit within the framework of known physics once the correct model was identified. When the accelerating expansion of the universe was discovered in 1998 through observations of distant supernova, it was unexpected and implied the existence of dark energy, a form of energy with negative pressure that drives the acceleration. This was a major surprise, but the observations were robust, replicated by multiple teams, and the interpretation, while requiring a new component to cosmology, did not violate fundamental physics. Time-reversed matter would be in a different category. It would not merely add a new component or object, but would challenge the causal structure of the universe. Let us consider the scenario once more from the standpoint of Bayesian reasoning. Bayesian inference combines prior probability with the likelihood of data given a hypothesis to produce a posterior probability. The prior probability of time-reversed matter, based on our current understanding of physics and the absence of any previous observation of such a phenomenon, is extremely low. The likelihood of a dataset that appears to show time-reversed behavior, given that instrumental artifacts, misinterpretations, or astrophysical illusions are common, is relatively high. The likelihood of the same dataset, given that time-reversed matter is real and was observed, is difficult to assess without a detailed model. But even if we grant it is high, the posterior probability would still be low because the prior is so low. To shift the posterior probability significantly, the evidence would need to be overwhelming. Multiple independent datasets, all inconsistent with any other explanation, and all pointing to the same conclusion. A single ambiguous observation, no matter how intriguing, is insufficient. As we push deeper into the hypothetical, imagine that decades from now, after extensive observation and theoretical development, a consensus emerges that certain astrophysical systems do exhibit time-reverse dynamics under specific conditions. What would the universe look like? There might be regions or epochs where the arrow of time is locally inverted, perhaps associated with exotic matter created in the early universe or by advanced processes in the late universe. These regions would be rare and isolated to prevent causal paradoxes from propagating globally. Observers within such a region might not perceive anything unusual because their own arrow of time, including memory formation and perception, would be aligned with the local dynamics. Only external observers, like astronomers using Webb, would detect the anomaly. The boundary between normal and time-reversed regions would be a subject of intense study. How is causality preserved? How do signals cross the boundary? Are there observable phenomena like a distinct emission signature or a distortion in spacetime that mark the boundary? Such a universe would necessitate revisions to cosmology. The initial conditions of the Big Bang would need to accommodate the eventual formation of time-reversed regions. Or there would need to be a mechanism by which time's arrow can locally flip during cosmic evolution. The thermodynamic history of the universe would be more complex, with entropy increasing in some regions and decreasing in others, requiring a careful accounting to ensure global entropy still increases or remains consistent with the laws of thermodynamics as generalized. Particle physics might need to incorporate new fields or interactions that mediate time reversal. All of this is highly speculative, a castle built on a foundation that does not yet exist, but it illustrates the magnitude of the implications if the claim were true. From a practical standpoint, if Webb has captured data that are being interpreted as matter moving backwards in time, the first order of business is to make the data and analysis fully transparent. Publish the raw data, the calibration files, the reduction scripts, and the analysis code. Invite independent researchers to examine every step. Encourage alternative interpretations. Hold workshops and invite skeptics to present challenges. This is the scientific method at work. A claim is made, tested, and either confirmed or refuted through rigorous investigation. The process can be slow and contentious, but it is the best tool humanity has for distinguishing truth from error. The role of funding and institutional support is also relevant. Major discoveries require resources for follow-up observations, theoretical work, and community engagement. If an initial observation is intriguing but not conclusive, funding agencies might be hesitant to invest in follow-up without stronger evidence. On the other hand, the potential payoff of confirming a revolutionary discovery is so high that some level of risk-taking is justified. Balancing the need for rigor with the willingness to explore unexpected results is a challenge for the scientific community and funding bodies. Communication with the public is another dimension. Astronomy captures the imagination, and news of discoveries spreads rapidly through media and social networks. Sensational headlines can create misconceptions and unrealistic expectations. Scientists have a responsibility to communicate clearly, distinguishing between confirmed findings, tentative results, and speculative hypotheses. A headline that states, James Webb just captured matter moving backwards in time without qualifiers is misleading if the evidence is preliminary or ambiguous. A more accurate headline might be, Webb observes unusual dynamics in distant galaxy. Researchers investigating, or anomalous light curve prompts questions about time and causality. The challenge is that nuanced headlines are less attention-grabbing, and media outlets are incentivized to maximize clicks. Scientists and science communicators must navigate this landscape carefully, advocating for accuracy while recognizing the realities of public communication. Education also plays a role. A public with a strong foundation in science literacy is better equipped to evaluate extraordinary claims critically. Understanding the difference between observation and interpretation, the role of models and assumptions, and the nature of scientific uncertainty helps people appreciate the process by which science advances. When a surprising claim is made, an informed public can ask the right questions. What is the evidence? What are the alternative explanations? Has the result been replicated? What do other experts say? This critical thinking is a defense against both unwarranted skepticism, which dismisses genuine discoveries prematurely, and unwarranted credulity, which accepts sensational claims without scrutiny. Let us now circle back to the instruments themselves and consider their limitations in more detail. Webb's detectors have a finite dynamic range. They can measure brightness from the faintest detectable sources, limited by detector noise and cosmic background, to the brightest sources, limited by saturation where the detector can no longer count photons accurately. For very bright sources, such as nearby stars, special techniques like subarray readouts or filters that reduce the incoming light are used. If a source is too bright, the detector saturates, and the measured brightness is lower than the true brightness. More importantly, saturated pixels can bleed charge into neighboring pixels, creating artifacts. If these artifacts are not properly flagged in the data processing, they could be mistaken for real structure. A time series of images with saturation artifacts could show false brightness variations or spurious motion. Detector persistence is another effect. After a bright source is observed, a residual image can remain on the detector for subsequent exposures. This is because charge can become trapped in the detector material and is slowly released. Persistence can create ghost images in later frames, which could be confused with real sources if not accounted for. Calibration software attempts to model and subtract persistence, but the correction is imperfect, especially for very bright sources. If persistence is mistaken for a real object, and if the object appears in different locations in different frames due to the varying persistence pattern, it could create the illusion of motion that is not real. Cosmic rays are a constant challenge. High-energy particles strike the detectors continuously, leaving bright streaks or spots. Most cosmic rays are easily identified and rejected because they have a characteristic appearance. They are bright, localized, and appear in only one of several dithered or repeated exposures. However, a small fraction of cosmic rays can mimic real sources, especially if they happen to strike the detector at the location of a real faint source, boosting its brightness. If a time series observation has a cosmic ray hit in one frame, that frame will show an anomalously bright measurement. If the cosmic ray hit is not rejected, the light curve will have a spurious spike. If multiple cosmic rays hit the same location by coincidence in different frames, which is extremely unlikely but not impossible in a large dataset, the light curve could show repeated spikes that might be mistaken for a real variability pattern. Scattered light is another issue. Light from bright sources outside the field of view can scatter off the telescope optics and detectors, creating diffuse background light or ghost images. Webb's design includes baffles and shields to minimize scattered light, but it cannot be eliminated entirely. Bright planets, stars, or the Earth and Moon can be sources of scattered light if they are near the field of view. The scattered light pattern depends on the geometry and can vary between observations if the telescope pointing changes. If scattered light is mistaken for emission from the target, the measured brightness and spectrum will be incorrect. In a time series, varying scattered light could create false variability. Detector flat fields, the pixel-to-pixel sensitivity variations, are calibrated using observations of a uniformly illuminated field. However, the flat field can change over time due to detector aging, contamination, or other effects. If the flat field is not updated or if the calibration is poor, sources at different locations on the detector will have systematically wrong brightnesses. If a source moves across the detector due to dithering or pointing changes, its measured brightness will vary even if the true brightness is constant. This is a source of false variability that must be corrected in the data processing. Wavelength calibration in spectroscopy relies on observations of calibration lamps with known emission lines or on observations of astronomical sources with known spectral features. If the wavelength solution drifts due to thermal changes or instrument flexure, the mapping from detector pixels to wavelengths will be incorrect. This causes spectral features to appear at wrong wavelengths, leading to incorrect Doppler shift measurements. In a time series of spectra, a drifting wavelength solution could cause a spectral line to appear to shift, even if the source velocity is constant. This would create a false velocity trend that could be mistaken for acceleration, oscillation, or other dynamics. Pointing jitter and drift introduce astrometric errors. Webb uses guide stars to maintain its pointing, but the accuracy is limited. Small pointing errors cause the image of a source to shift on the detector between exposures. If the shifts are not correctly measured and compensated, the source position will appear to change, creating false proper motion. In a time series, this could create a trajectory that does not represent the true motion of the source. If the errors are random, they will average out with enough observations. But if there is a systematic trend, such as a thermal drift over the course of a long observation, the trajectory could have a systematic bias. All of these instrumental effects are known and studied. The Webb team has characterized them through extensive ground testing and on-orbit commissioning. Calibration pipelines include corrections for each effect, and data quality flags alert users to potential problems. However, no calibration is perfect, and residual errors remain. For most science, the residuals are small compared to the astrophysical signal and do not affect the conclusions. For a claim as sensitive as detecting time-reversed matter, however, even small residuals could be significant. The analysis would need to demonstrate that instrumental effects are negligible compared to the claimed signal, or that the signal is robust against plausible ranges of instrumental errors. This requires careful error analysis, including systematic uncertainties, not just statistical uncertainties from photon counting. Let us explore another astrophysical phenomenon that could create confusing observations: binary systems and eclipses. A binary star system consists of two stars orbiting their common center of mass. If the orbit is edge-on as seen from Earth, the stars periodically eclipse each other, causing the total brightness to dip. The light curve of an eclipsing binary has a characteristic shape: a dip when one star passes in front of the other, a recovery when the eclipse ends, a second dip if the orbit is circular and the stars are similar in size, and a repeat of the pattern with a period equal to the orbital period. If Webb observes an eclipsing binary and the light curve is misinterpreted, one might incorrectly infer dynamics. For instance, if only a partial orbital phase is observed and the periodic nature is not recognized, the brightness variations might be mistaken for an intrinsic variability or transient event. Now consider a triple system or a system with a circumbinary disk. The dynamics become more complex. The stars and disk can interact, leading to precession, tidal effects, and variable obscuration. The light curve and spectrum can show complex, time-dependent behavior. If the system's geometry is not correctly understood, The observed variations might seem to defy simple explanations. An extreme case, a disk with a warp or spiral structure that rotates, causing different parts of the disk to obscure the central stars at different times. The obscuration pattern could create brightness variations that rise and fall in a manner that superficially resembles a reversed process if the geometry is not appreciated. Planetary transits offer another example. When an exoplanet passes in front of its host star, it blocks a small fraction of the star's light, creating a shallow dip in the light curve. The shape of the dip provides information about the planet's size, orbital speed, and atmosphere if observed at high precision. If the planet has a highly eccentric orbit, or if there are multiple planets in the system with orbital resonances, the transit times can vary in complex ways. Transit timing variations are used to detect additional planets in the system through their gravitational perturbations. If the timing variations are not correctly modeled, one might infer incorrect orbital dynamics. A planet appearing to transit earlier than expected could be mistaken for retrograde motion if the model is wrong. Gravitational microlensing presents a phenomenon where a foreground object, such as a planet or brown dwarf, passes in front of a background star and magnifies it through gravitational lensing. The magnification rises as the foreground object approaches alignment, peaks at closest approach, and falls as it moves away. The light curve is symmetric if the alignment is perfect and the lensing object is a point mass. However, if the lensing object has a companion, such as a planet orbiting a star, the light curve can have additional features, bumps or dips, superimposed on the main magnification. These features provide information about the companion's mass and orbital separation. If a microlensing event is observed and the light curve shows a complex shape, careful modeling is required to interpret the features. An incorrect model might lead to an incorrect mass or trajectory for the lensing object, but this is a failure of modeling, not a physical anomaly. Asteroids and comets within our solar system move across the sky and can photobomb observations of distant objects. If Webb is observing a faint galaxy and an asteroid happens to pass through the field, the asteroid will appear as a moving source that changes position between exposures. The asteroid's trajectory can be determined from multiple observations and used to predict its future and past positions. If an asteroid is mistaken for a feature of the distant galaxy, or if its motion is not recognized, it could create confusion. However, asteroids move in predictable orbits governed by Newtonian mechanics, and their motion is always forward in time. There is no possibility of an asteroid moving backwards in time, barring a complete overhaul of physics. Solar system objects also remind us that motion is relative. The planets orbit the sun, and from Earth's perspective, they sometimes move prograde, eastward against the background stars, and sometimes retrograde, westward, as Earth overtakes them or they overtake Earth. This retrograde motion is an apparent motion due to the relative orbital velocities and is well understood since ancient times. The Ptolemaic model of the solar system attempted to explain retrograde motion with epicycles, complex circular orbits within orbits. The Copernican heliocentric model provided a simpler explanation. Retrograde motion is a projection effect. Similarly, many astrophysical phenomena that seem complex or reversed when viewed from one perspective can be understood simply when the correct geometry is recognized. Let us now address the question of how one would definitively prove time-reversed motion if it were observed. What would constitute irrefutable evidence? First, the observation would need to be reproducible. Multiple independent observations of the same object or of similar objects should show the same behavior. Second, the behavior must be inconsistent with all known physical processes operating in forward time. This requires exhaustive modeling. Simulate every plausible scenario: lensing, light echoes, intrinsic dynamics, projection effects, instrumental artifacts, and show that none can reproduce the observation. Third, the time reversed behavior must make testable predictions that are confirmed. For instance, if matter is truly reversing in time, then entropy should be decreasing, and this should be detectable through spectroscopic signatures of temperature and density evolution. Fourth, the mechanism for time reversal must be identified and be consistent with a broader theoretical framework, even if that framework is speculative. Without a mechanism, the claim remains a phenomenological description without explanatory power. Fifth, the observation should be cross-validated with other instruments and wavelengths. If Webb observes time-reversed dynamics in the infrared, do X-ray, radio, and optical observations show consistent behavior? If other telescopes see nothing unusual, that suggests the effect is specific to Webb's observations, pointing to an instrumental or analysis issue. Sixth, the statistical significance must be high. With the large volume of data from modern surveys, rare statistical flukes will occur. A single 5 sigma detection is interesting but not definitive. Multiple detections at high significance, or a single detection at much higher significance, say 10 sigma or more, would be more convincing. Finally, independent teams should analyze the data and reach the same conclusion. If one team claims time reversal and another claims a conventional explanation fits the data, the community will need to resolve the disagreement through further observation and debate. Even with all these criteria met, there would still be skepticism, and rightly so. Extraordinary claims require extraordinary evidence, a phrase popularized by Carl Sagan. The more a claim challenges established knowledge, the higher the burden of proof. Time-reversed matter challenges not just a single theory, but the entire edifice of physics built over centuries. It would be the most profound discovery in the history of science, dwarfing even the discovery of quantum mechanics or general relativity, because it would force a reconceptualization of causality itself. The skepticism is not obstinacy, but prudence born of experience. History is filled with claims that seemed extraordinary, but turned out to be error. The scientific community is conservative in the best sense. It conserves hard-won knowledge and demands rigorous proof before discarding it. Let us imagine the process unfolding in real time. A research team analyzing Webb data notices an anomaly in the light curve of a distant object. The anomaly does not fit standard models. They check the data processing and find no obvious errors. They consult colleagues who are intrigued but suggest alternative explanations. The team performs additional analyses, rules out some alternatives, but cannot definitively rule out all. They write a paper describing the anomaly and proposing time-reversed matter as one possible explanation among several. The paper undergoes peer review. The reviewers are skeptical and request more rigorous checks. The team provides additional analysis. The paper is eventually published in a journal, perhaps with a cautious abstract that emphasizes the anomaly is unexplained and invites further investigation. News of the paper spreads. Other astronomers download the Webb data and reanalyze it. Some find the same anomaly and confirm the initial team's data reduction. Others find ways to explain the anomaly with conventional physics or identify an overlooked instrumental effect. Debates occur at conferences. Proposals are submitted for follow up observations with Webb and other telescopes. Some are approved, others are not due to limited observing time. The follow up observations are performed. If they show the anomaly is reproducible and consistent, interest intensifies. If they show the anomaly was a fluke or is explained conventionally, interest wanes. Years pass, dozens of papers are written. A consensus gradually emerges, either that the phenomenon is real and requires new physics, or that it has been explained and is not extraordinary. This is the slow, grinding machinery of science. Hypothesis, test, debate, revise, repeat. It is not dramatic and it does not produce instant answers, but it works. The process filters out errors and converges on truth, or at least on models that predict observations with ever increasing accuracy. A claim of time-reversed matter would be subjected to this process, and only after years of scrutiny would it be accepted or rejected. Now let us consider the broader context of time in cosmology. The universe began, according to the prevailing Big Bang model, approximately 13.8 billion years ago in a hot, dense state. Time itself is often said to have begun at the Big Bang, though this is a statement about the applicability of our current theories, rather than a definitive ontological claim. General relativity describes the universe's expansion, but near the Big Bang singularity, quantum effects become important, and general relativity breaks down. A complete theory of quantum gravity is needed to describe the very earliest moments, the Planck epoch. Various proposals exist: inflationary cosmology, loop quantum cosmology, string cosmology, but none are confirmed. Some models suggest time could be emergent, not fundamental, or that the Big Bang is not the absolute beginning, but part of a larger, possibly cyclic process. If time is emergent, what does it mean for matter to move backwards in time? The question becomes less clear. If time is a property that arises from the collective behavior of more fundamental entities, then time reversal might be a rearrangement of those entities such that the emergent time parameter decreases. This is highly speculative and far from any observational test Webb could perform. The observations Webb makes are in the classical regime where time is well defined. Space-time is a smooth manifold, and causality is clear. Any exotic quantum gravitational effects are suppressed by the Planck scale and are not accessible to current instruments. The cosmological constant or dark energy, which drives the accelerated expansion of the universe, introduces its own puzzles related to time. Dark energy appears to have a constant density even as the universe expands, which means its total energy increases as the volume of the universe increases. This seems to violate energy conservation, but in general relativity, energy conservation is subtle and depends on the space-time geometry. In an expanding universe, energy is not conserved globally in the same way it is in flat spacetime. Dark energy's equation of state relates its pressure to its density. For a cosmological constant, the equation of state parameter W equals -1. Other models of dark energy have different values of W, and some allow W to vary with time. If W were less than -1, the dark energy would be phantom energy, causing a big rip scenario where the universe's expansion accelerates so much that galaxies, stars, atoms, and eventually space-time itself are torn apart. Phantom energy has properties that seem to violate energy conditions and might be associated with exotic physics, But even phantom energy does not cause time to run backwards. It is still a forward evolving process, just with unusual thermodynamic properties. The role of symmetry in physics is central. Symmetries lead to conservation laws via Noether's theorem. Time translation symmetry leads to energy conservation. Space translation symmetry leads to momentum conservation. Time reversal symmetry, denoted T, is the idea that the fundamental laws of physics are unchanged if time is reversed. In classical mechanics, Newton's laws are time reversal symmetric. If you reverse the velocities of all particles and run the system backwards in time, it follows the same laws. However, macroscopic systems are not time reversal symmetric because of the second law of thermodynamics. In quantum mechanics, time reversal is an anti-unitary operation, involving both reversing time and taking complex conjugates. Most fundamental interactions respect T-symmetry, but the weak nuclear force violates CP symmetry, charge conjugation times parity, and by the CP-T theorem, which states that the combined operation of CP and T is a symmetry of any quantum field theory. This implies a small violation of T-symmetry. However, this T violation at the fundamental level does not translate to macroscopic time reversal. It affects certain rare particle decays, but does not allow entropy to decrease globally or causality to be violated. If Webb were to observe a process that violates time reversal symmetry in a new way, it would be of great interest to particle physicists, but it would not be the same as observing matter moving backwards in time. A T-violating process is one where the process and its time-reversed counterpart occur at different rates or have different properties. This is a forward time phenomenon. It does not involve a trajectory that loops back in time. The distinction is crucial and often confused in popular discussions. Let us also address misconceptions about antimatter. Antimatter particles, such as positrons and antiprotons, are produced in high-energy processes and have been created and studied in laboratories. Antimatter has the same mass as matter but opposite charge. When matter and antimatter meet, they annihilate, converting their mass to energy via E equals mc squared. The Feynman-Stueckelberg interpretation of antiparticles as particles moving backwards in time is a mathematical tool, not a physical description. In all observable respects, antiparticles move forward in time just like ordinary particles. If Webb were to observe an astronomical source emitting antimatter, it would be scientifically interesting. There is an unsolved mystery about why the universe is dominated by matter rather than antimatter. But it would not be evidence of time reversal. The antimatter would be moving forward in time, expanding outward from its source, just like matter. Another potential source of confusion is tachyons, hypothetical particles that move faster than light. In special relativity, if a particle could move faster than light, there would be reference frames in which it moves backwards in time. Tachyons have never been observed, and their existence would lead to causality violations and paradoxes. Most physicists believe tachyons do not exist. If a Webb observation suggested motion faster than light, it would almost certainly be an illusion due to projection or beaming effects, as discussed earlier with superluminal jets, not actual faster-than-light motion. The concept of superluminal expansion in cosmology is also worth clarifying. During the inflationary epoch, the universe is thought to have expanded exponentially, with regions of space separating faster than the speed of light. This does not violate relativity, because it is space itself expanding, not matter moving through space. The speed of light limit applies to motion through space, not to the expansion of space. Similarly, distant galaxies are receding from us faster than the speed of light due to the Hubble expansion. Yet, this is not a violation of relativity, and it does not involve backwards time motion. The galaxies are moving forward in time. Their light is traveling forward in time, and we observe them in the distant past due to light travel time. Let us circle back to the specific capabilities of Webb in terms of time domain astronomy. Webb is not optimized for discovering transients. It has a narrow field of view and is typically pointed at predetermined targets. Ground-based surveys and other space missions, such as the Zwicky Transient Facility or the upcoming Vera Rubin Observatory, are better suited for finding transients. However, once a transient is identified by another facility, Webb can perform follow-up observations to study it in detail, especially in the infrared where Webb excels. If a transient exhibited time-reversed behavior, Webb's data would be crucial for understanding it, but the discovery would likely come from a survey telescope. Webb's time resolution capabilities vary by mode. In imaging, the shortest practical exposure time is a few seconds, limited by detector readout and data rates. This is sufficient for most astronomical sources, which vary on much longer timescales. For very rapid phenomena, such as the dynamics near a black hole event horizon or the emission from a pulsar, even higher time resolution would be needed, down to milliseconds or microseconds. Webb is not designed for such observations. Specialized instruments on other missions, such as X-ray timing satellites, are used for those studies. This limitation means Webb is unlikely to be the instrument that discovers a rapid time reversal event, if such a thing exists. It could, however, observe slower processes where the time evolution over days, weeks, or months shows anomalous behavior. The data from Webb will be analyzed for decades to come. The archive will grow as more observations are taken, and future astronomers will mine it for discoveries that the original observers did not anticipate. It is possible that an anomalous observation is sitting in the Webb data already, unnoticed, waiting for someone to find it. The history of astronomy has many examples of serendipitous discoveries: pulsars, gamma-ray bursts, gravitational lensing, dark energy. Each of these was found by researchers looking at data carefully and noticing something unexpected. If matter moving backwards in time is observable, it may already be in the data, or it may be observed in the future. The key is to keep an open mind while maintaining rigorous standards of evidence. As we approach the natural conclusion of this exploration, we recognize that the question, "Has James Webb captured matter moving backwards in time?" is not a question that can be answered with a simple yes or no. It is a question that unpacks into layers of sub-questions. What do we mean by captured? What do we mean by matter? What do we mean by backwards in time? What would constitute evidence? How would we rule out alternative explanations? The process of addressing these questions reveals the depth and rigor of the scientific method, the complexity of modern astrophysics, and the care with which extraordinary claims must be evaluated. If Webb has indeed observed something anomalous, the anomaly is almost certainly explicable within known physics or as an artifact of observation and analysis. The probability that it represents a genuine violation of causality or reversal of time's arrow is vanishingly small. Yet science progresses by investigating anomalies, no matter how unlikely they seem to be revolutionary. Each investigation, even if it concludes that the anomaly is mundane, deepens our understanding of the instruments, the data, and the universe. The investigation itself is valuable. The universe as revealed by James Webb is already full of wonders that stretch our comprehension. Galaxies that formed when the universe was only a few 100 million years old. Exoplanet atmospheres with the potential for biosignatures. Nebulae sculpted by stellar winds into shapes of haunting beauty. Black holes whose gravity warps the fabric of spacetime. These wonders are real, confirmed by rigorous observation and analysis. They inspire awe and drive us to learn more. Adding to that list, a phenomenon as extraordinary as time-reversed matter would be the discovery of the millennium, but it would need to meet the highest standards of evidence. Until and unless such evidence is presented, we observe the universe moving forward in time, obeying the laws of physics as we understand them, revealing its secrets one photon at a time. The dance of light and matter across the cosmos, the silent journeys of photons from distant sources to the detectors of Webb, the patient work of scientists and engineers who build the instruments and analyze the data. All of this proceeds forward, step by step, discovery by discovery. The story of the universe unfolds in time's arrow from past to future, and we, as observers, follow that arrow, using our tools and our minds to read the history written in light. Whether matter can move backwards in time remains an open question in the realm of speculative physics. But as of now, as the data flow from Webb and are scrutinized by thousands of eyes, the universe continues its ancient expansion. Stars ignite and die. Galaxies merge and evolve, and time, as far as we can measure and understand, flows ever forward into an open and uncertain future, carrying us along with it.